have access to all the videos. Yeah, there you go. All right, so A1, atomic theory and nuclear. So remember how I told you a couple weeks ago that if you're writing everything you see on the screen, you're doing it wrong? Well, I'm going to remind you, if you're writing everything you see on the screen, you're doing it wrong. What you should be doing is reading what's on the screen, hearing what I'm telling you, imagining the analogy, and then writing it in your own words. If you cannot write something in your own words, you do not understand it. Okay? And if you do not understand it, you have questions to ask. Please ask them. Okay? So, read, hear, imagine, and write things in your own words. If you can't do that, you don't understand the concept, you're not prepared, and you should be asking questions. Okay. Give me thumbs up if that concept idea makes sense. Okay, I'm getting about 2/3, 5, 6, good. All right. So, atoms. So today we're going to talk about atoms, elements, and compounds. We're going to talk about parts of the atom we call subatomics. And then we're going to talk about nuclear. A large chunk of this should actually be review, because you've seen a lot of this in previous units. Okay. Are there any questions before we jump right in? No? Okay. So, chemicals. The simplest building block of matter is the what? The atom. The atom is the simplest building block of matter. There are about 90 that we can find on the planet. About everything after 92 is artificial, and then in addition to everything after 92, promethium and technetium are also artificial. So there's about 92 elements until uranium, about 90 naturally occurring elements. Everything after uranium is made in the lab. Most of the time, it's not useful at that point either. So atoms are the simplest building block of matter. Elements are sometimes just the atom, and sometimes they're two atoms. Diatomic atoms are never found alone. So I'll let you scribble that down, then we'll talk about diatomics a little bit more. So one of the things we find is carbon, hydrogen, oxygen, nitrogen, and phosphorus are in all living things. Anyone have any idea why they're in all living things? This is trivia. Not going to be tested on it. They're in DNA. Yeah, they're in DNA. So if something is living, it's got DNA, so it's got to have carbon, oxygen, nitrogen, and phosphorus. So I will have the periodic table up, hopefully, during 6th period. I've got the lanthanides and actinides up. We'll have the rest of it put up, hopefully, during 6th period, and we can refer back to it. It's like, hey, look at that. But in the meantime, it might not be a bad idea to have your periodic table out, so you have something to refer to. We're not going to study it, but it is kind of nice to have a little visual aid in front of you while you're taking your notes. So 90 elements are naturally occurring. We can find them on the planet. Everything after 92 is artificial. Neptunium, plutonium, americium, californium, those are all artificial. We made them in a lab. And they're not really good for anything unless you want to knock down buildings with a nuclear bomb. Or, you know, if we need something radioactive, then they're great. Otherwise, not really great. Now here's the important thing. Diatomic. What does di mean? Two. Okay? Like you write your die cycle all around? Okay? Diatomic. Diatomic elements are never found alone. And they do have a fun little mnemonic. It's an acronym, or I guess, not really an acronym, but it's a fun little mnemonic. It's Brinkelhoff. Brinkelhoff. If you're in the front row, it's right there. Brinkelhoff. There are 7 elements that are never found alone. They will either be found in a compound or with something like with itself. They'll either be in a compound or they'll be bound to itself. You're never going to see just a bromine all by itself. It's going to be in a compound or it's going to be bound to another bromine. Same for iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. You'll never see oxygen all by itself. It'll have to be bound to something else, with a few exceptions in the upper atmosphere where things get a little crazy. Okay? So they're diatomic. We're going to be doing balancing chemical reactions later on. It's going to be very important to remember the Brinkelhoffs. You're never going to have hydrogen all by itself. It'll have to be in a compound or bound to another hydrogen. Okay? Does that idea make sense? Give me a thumbs up if that idea makes sense. Okay. Some of you are scribbling. I'll give you a few seconds to finish scribbling. And again, please don't write down everything you see. Put it in your own words. Now, if you're handling something and it's not an element, like I could give you a block of iron, and for the most part, every element in that block is iron. Okay? Block of iron. If you're not handling atoms or elements, what are you handling? Starts with a C. Compounds. Yeah. Compounds are made of 2 or more elements. So if you're not handling elements, you're handling compounds. Okay? Compounds are made of 2 or more elements. And here's the zany thing about compounds. Their properties are nothing like the elements that make them up. Nothing like them. They're always very different. For instance, you've all encountered H2O. Hydrogen at room temperature is what phase? It's a gas, yeah. Like the Hindenburg. Okay. Hydrogen at what phase, or hydrogen at room temperature is a gas. Oxygen at room temperature is what? A gas. 21% of the air you're breathing is oxygen. You put them together, and you get something that at room temperature is not a gas. You get water. The properties of water are nothing like the properties of hydrogen or oxygen. Fun fact, you've probably never seen elemental sodium, but you will. We're going to have some elemental sodium. I'm going to show you what that does. It's a metal. Yeah. Sodium is a metal. It's very soft. You could squish it in your hands like hard Play-Doh. And it reacts explosively with water. Yeah. We're going to put it in water. It's going to go shh, pow! Later on. Not today, but later. Yeah. So that's sodium. Very dangerous, explosive metal. Chlorine. You probably encountered small amounts of chlorine above a swimming pool. But for the most part, chlorine is a yellow gas that will attack your mucous membranes in your lungs. It was used in World War I as a weapon. They would get chlorine canisters and a grenade, and they'd throw it as far as they could and try to get into the trenches. Because the soldiers would be behind the trenches. And they'd look out, and they'd shoot. Well, if they didn't get their gas mask down in time, they'd be like, and then you'd run up there and you'd shoot them. Because they wouldn't be able to shoot back. So chlorine was actually used as a weapon. So you get this explosive metal and this dangerous chlorine gas, and you put them together, and you get something you put on your French fries. Salt. NaCl is just table salt. NaCl is just table salt. Put it on your popcorn too. And then there's this one. This is iron oxide. Iron, you might recall, is a very hard metal. Very, very hard, but malleable. Oxygen's a gas. You put them together, and you get this red powder that's not really good for anything. This is rust. Okay? So the properties of compounds have nothing to do with the properties of their elements. Pretty slick. It's one of the reasons chemistry is so cool. Okay, questions? Thumbs up, you're good with me? Ready to move on? Moving on. Okay. So, the parts of the atom. Who can volunteer a part of an atom? The nucleus. And inside the nucleus we have the protons and the neutrons. And then zooming around the protons and neutrons we have the electrons. Okay, so it's nice that you remembered your previous classes. Okay, so you got the protons. Protons have a charge of +1 and a mass of 1. Neutrons have a mass of 1, but a charge of nothing. And electrons have a mass of almost nothing and a charge of -1. Now I say electrons have a mass of almost nothing. I'm going to talk about why that is on Friday. Why it's actually not 0, even though we round it down to 0. It's not 0, we round it down to 0. So we tend to say it's 0, but it's not. I'll talk about that on Friday. So we have a proton, we have a neutron, and we have an electron. Protons have what charge? Positive. Neutrons have what charge? Negative. and electrons are negative. Or sorry, neutrons are neutral and electrons are negative. Now this you've noted, you've seen this years ago, and oh, fun thing, we call the protons and the neutrons nucleons because they're in the nucleus. We say, they're nucleons, because they're in the nucleus. Now, this is the way atoms are usually shown in textbooks and movies and stuff. This is nothing like real life. Nothing like it. Well, let's pretend that this is a proton. This is a proton, and we're going to make the hydrogen atom. The hydrogen atom has one proton and one electron. This BB is an electron. This is a proton. If we were to set our proton, or make a hydrogen atom, which is composed of one proton and one electron, we're going to set this atom, or this nucleus, on the 50-yard line in the middle of a football field, right in the middle of the cowboy star. Where would we put the first electron? Would we put it at the 40-yard line, the 30-yard line, the 20-yard line, the 10-yard line, or the goal line? The goal line. Yeah, that is how empty the atom is. If this was the proton on the 50-yard line, this little electron is on the goal line. And what's between the electron and the proton? Nothing. Nothing. There's nothing. Air. No, not air. Nothing. There's nothing. It's void. There's completely nothing between it. Most of us is nothing. Most of you, nothing. Most of me, nothing. Most of this whole world is nothing. In fact, if you were to take the entire world and somehow suck out all the space and cram everything that has mass together, it could fit in this room. It could probably fit in your bedroom. That's how empty the world is. If you were to somehow take out all the space, it could probably fit in your bedroom, unless you're Harry Potter. It could fit in there. Now, why is it, if most of the world is empty space, why can't I put my hand right through this table?
Because the nucleus themselves are repelling each other.
Exactly. Well done. So, you know the single most important concept in all of physical science is that opposite things do what? Attract. But similar things do what? Repel. So the opposite charged things attract, while the similar things repel. So around, on the outside of all the atoms that make up my hand are what? Electrons. And around the outside of the atom of everything that makes this table are what? Electrons. And they repel each other. I can't put my hands through the table because the electrons that make up around the atoms that make up my hand are repelled by the electrons that make up the table. That's what space is. That's what volume is. Volume is simply electrons that are repelling each other. They don't want to repel. They're like repelled. Okay. So if that makes sense, and hopefully, give me a thumbs up if that makes sense to you.
Yeah.
If that makes sense to you, then there should be something you should be kind of itching about. And that is, if similar things repel, how is it the electrons are stuck, or sorry, the protons are stuck in the nucleus? Shouldn't the protons repel each other? But they're stuck in the nucleus. Why are the protons, which are strongly repelled by each other, stuck in the nucleus? The neutrons. The neutrons form what are called, I'm not making this up, nuclear glue. The neutrons exchange between each other things that we just called gluons. We're not entirely sure what they are and how it works, so we just named the concept gluons. Neutrons are shooting these gluons between each other, and the protons are afraid of the gluons, so they stay put because they can't cross the gluons. So it's like a net of gluons that keep the protons together. Weird, huh? But that's how it works. So let's look at a carbon atom. A carbon atom has 6 protons. And if those 6 protons were all by themselves, that nucleus would fly apart. But luckily, there's a bunch of neutrons in between that hold them together. And those neutrons create a web of nuclear glue that holds the nucleus together. Without them, the protons would repel each other. Cool? Yep. Cool. We went on. Any questions? Question?
Why doesn't, like, the electron go to the nucleus that it's attracted to the proton?
It's moving really, really fast. It's an excellent question. So the question was, if you didn't hear it, why are the electrons not just falling into the nucleus? Because the nucleus, which is positively charged, is attracted to the electrons, which are negatively charged, and negatively charged electrons are attracted to the nucleus. The reason they do, because the electron is moving really, really fast. Okay, it's like a ball on the end of the tether ball. If you hit the ball, it'll stay away from the pole. If the ball runs out of energy, then it will fall into the pole. And then if an electron runs out of energy, it could fall into the nucleus. So, but that's cruising along almost at the speed of light, zooming around. Yeah.
So when there's an isotope that mixes in a neutron, is that why the decay? Because the protons are starting to push it apart?
Yep. Okay. So in a normal neutral, and we're going to talk about that very thing here in about 2 minutes. In a normal neutral unreacted atom, the number of protons is balanced by the number of electrons. So if you had your carbon atom, so here's my carbon atom. If you had my carbon atom that has 6 protons, around it would be 6 electrons for a grand total of plus 6 plus negative 6? 0. Yeah. Electrons are negative. So in a neutral unreacted atom, the number of protons is balanced by the number of electrons for a grand total of 0. If that is not the case, what you get is an ion. An ion is an atom that has more or less electrons than it has protons. An ion is an atom that has more or less electrons than it has protons. Hey Chris, would you like to move to the second row? Like we could move Chloe and Maddie in. You could sit right there, or you can move in that seat right there.
I'm fine right here.
Are you sure? Okay, because you're like twisting around. Okay, perfectly fine, as long as you're comfortable. Okay, so ions have more or less electrons than they have protons, which is great. So if you have 6 protons and 6 electrons, you have a 0 neutral atom. But what if you have 6 protons and 7 electrons? It's an ion. And what charge is the ion? Negative. This is one of the weird things that even very smart people like us tend to get off, tend to miss, and that is electrons are negatively charged. When you take away an electron, the atom becomes positive. When you add an electron, the atom becomes negative. Conceptually, we understand this, but in the heat of battle on a quiz, we tend to get this mixed up. So slow down and realize that 0 plus a negative 1 is what charge? Negative 1. And 0 minus a negative 1 is what charge? Positive 1. By taking away an electron, you make the atom positive ion. By adding an electron, you make the atom a negative ion. Cool? All right. Moving right along. Okay. Let's talk about isotopes. A nuclide is the name of a nuclear isotope. The nucleus of a nuclear isotope. Now, this is carbon-12. We say it's 12 because it has 12 units of mass in the nucleus. 6 protons and 6 neutrons. Okay. So you count it up, we got 6 protons and we got 6 neutrons for a grand total of 12. Make sense so far? Okay. Well, what if you had those same 6 protons and not 6 neutrons, but 7 neutrons? Yeah, if you had 7 neutrons and those same 6 protons, then you would have what's called an isotope. It's still carbon, but what's the mass of the carbon now? 13. Does that idea make sense?
Yeah.
because the mass is now 13. Isotopes are the same atom, same number of protons, but different numbers of neutrons. That's an isotope. There are carbons that have 8 neutrons. We call them carbon what? 14. There are carbons that have 5 neutrons. We call those carbon 6 plus 5 is 11, carbon 11. Okay, so there are lots of different isotopes of every element. As far as I know, pretty much every element has multiple isotopes. I might be wrong about that, but I'm pretty sure almost all of them do. Okay, give me a thumbs up if you understand the idea about isotopes. Ready to move on. Okay. Now, when we're writing isotopes, or nuclides, we place the mass up in the upper left. Mass goes in the upper left. Carbon 12, carbon 13. And we place the nuclear charge in the lower left. What would the nuclear charge be of this carbon atom? The nuclear charge. 6. Yeah. There are 6 protons, so we would place a 6 right there. The nuclear charge of a carbon atom's nucleus is 6 because all carbon atoms have 6 protons. Let me say that again in parentheses. All carbon atoms have 6 protons. In fact, write this down, put a star around it, maybe make it on a flag where a ninja is carrying it across the field, or put it in like, a shirt, like draw a guy with a shirt and put it on the front. The number of protons is the atomic number. The number of protons is the atomic number. The number of protons is the atomic number. This is so cool, because what this means is if you look at the periodic table and it tells you oxygen has an atomic number of 8, then every oxygen atom has how many protons? 8. If you look at neon and it tells you the atomic number is 10, then every single atom of neon has how many protons? 10. Every single one. If an atom doesn't have 10 protons, it's not neon. If an atom doesn't have 8 protons, it's not oxygen. And if an atom doesn't have 6 protons, it's not carbon. Question?
So if you were to add like 1 proton to lithium, it would turn into beryllium?
Exactly right. Yeah. So the question was, if you were to add, or the comment was, if you were to add 1 proton to lithium, would it become beryllium? Yes. Because all lithiums have 3 and all berylliums have 4. Capiche? Okay. Moving right along. Okay, so mass on top, nuclear charge down below. Decay. What is decay? Decay is when one thing turns into another thing. We have crazy words for it like transmutation. I don't care about that. What I care about is you understand that decay is what happens when one thing turns into another thing. And I'm going to show you the 3 or 4 primary modes of decay today. We'll pick up wherever we leave off, pick it up on Friday. But decay means one thing becoming something else. That's it. Now sometimes it might be really obvious. Sometimes it's not as obvious. Half-life is the time it takes for half of something to decay. The half-life of your cake is the time it takes for your friends to eat half your cake. So the half-life, if you have 100 grams of uranium and half of it becomes thorium, that's the time it takes for half of the uranium to become thorium. If you had 100 grams of something and it took a day to become 50 grams of that stuff, the half-life is 1 day. If you had 50 grams of something and it took 2 hours to become 25 grams, the half-life would be 2 hours. Now, if you look on internet tutorials, there are some crazy math, there's some crazy math on half-lives with natural logarithms. We're not going to use those. The math that we're going to use in this class is 1/2 raised to a power. That's it. Let me give you an example. If you have 100 grams, and then it becomes 50 grams, how many half-lives went by? 1. And then it becomes 25 grams, how many half-lives went by? 2. If you have 12.5 grams, how many half-lives went by? 3. If you have 6.25, how many half-lives went by? 4. So 1/2 to the first power is 1/2. 1/2 to the second power is 1/4. 1/2 to the third power is 1/8. That's the math we're doing for half-life. That's it. And we'll start that on Friday. We have a really cool simulation tomorrow where we build atoms. We just add protons and neutrons and electrons and build the atom. So we're doing that tomorrow. We'll talk more about half-life and do the math of half-life on Friday. Okay, give me a thumbs up if you're ready to talk about decay types. Any questions? Then we move on. Okay. There are 4 primary types of decay. In reality, there's lots of different decay. You are going to be responsible for 4 of them. The 4 most common. The first one, and the most common,